Hello together, my name is Andreas Muck from SPH, and I would like to introduce the ThermBooster, so the steam producing heat pump which we have developed, and say maybe a few general words about heat usage in the future. So let me start with the slides. The other way. If you would like to be more energy efficient in the future, and if you would like to produce heat, then we have a couple of options. And so if we compare the options which we do have in order to produce heat CO2 neutral, we can go to hydrogen, we can go to biomass, we can do direct electrification, and we can use heat pumps. And if we look onto the efficiency of the processes, we clearly see that so hydrogen, if you burn it, you are close to 1, but you need to produce the hydrogen. So means the primary energy efficiency of hydrogen just is in the range of 0.5. Biomass and direct electrification would mean that we are at an efficiency of maybe 1. If you go to heat pumps, depending on the temperature lift, we can achieve much higher efficiencies. And therefore, we think wherever it is possible to use heat pumps, we should use heat pumps because of the overall energy efficiency. So the efficiency which we can recycle doesn't need to be made new. Oh, sorry, wrong direction. So I guess most of you already know how a heat pump works, but let me quickly tell you the principle of a heat pump. So on one side we have the heat source, so means we get somewhere a certain temperature level into the heat pump, and then via a heat exchanger we evaporate a refrigerant, we compress it in the compressor, whereby it takes pressure and heat, and this heat is given to the condenser, where it is condensed, and then we have the expansion valve where it's expanded again, and here in the condenser the heat is given to the end user of the heat. Yeah, it's the same process as we have in every fridge at home. So nothing new. The new thing is that we are now able to produce temperatures which are much higher than before. So before I come to the ThermBooster itself, maybe a couple of words to our company. So SPH is a quite young company, so we are just 4 years old. So the company was founded in April 2020. We have now, we have one more, so it's 13 employees in the meantime. We received one new investor in 2021, which gave us the opportunity to build our test rig, to build our first unit, which has been tested for the last 2 years, up and down, in our test facility. And we have delivered beginning of last year the first units into the fields. I will come later to this project. We are located quite close to here, so just 20 kilometers from here, in Overath. We have structured the company in such a way that we concentrate on our strengths, because with such limited number of people, you can't do everything on your own. So the heart of the product is our compressor, which we have developed on our own. We are producing this compressor in our facilities, but the rest of the machine is assembled outside with a production partner, which we work with since a couple of years, so this works quite fine. So, as I said, the heart of our product is the compressor, which we developed from scratch, really. It's a 4-cylinder piston compressor with a theoretical displacement of approximately 580 cubic meter per hour. The high pressure side is designed for 35 bars, the low pressure side for 18 bars. It's an open design so that we can connect each and every electrical motor which we would like to use. And yeah, we are using electrical motors in the range between 110 and 200 kilowatts, depending on the needs for the application. Yeah, when we talk about refrigerants, currently we are mainly using HFOs, but we can also, and we will, use hydrocarbons in the future. We have one project which will be installed end of the year, beginning of next year, where we definitely will deliver the unit with hydrocarbons. But yeah, the rest of the units at this stage, the customers prefer to go with HFOs. As I said, due to the fact that we have this compressor newly developed and we have done high temperature heat pumps before, there are a couple of specific things which are really tricky with high temperature heat pumps. So handling of these HFOs together with the loop oil is very special. The HFOs are also very, very thick, so they have a very high viscosity, so means pressure drops in your compressors are higher than with other refrigerants. And we try to incorporate solutions here which yeah, cope with these challenges. So the valve system is completely new. We have also patented it. Also the oil handling, we have a oil conditioning system, which, as far as we know, nobody else is using in order to yeah, keep the viscosity of the loop oil always in a certain range, so that we have yeah, in all of the situations in the compressor, a good lubrication for the pistons and the bearings. Due to the fact that we are using frequency controlled electrical motors, and we are having a piston compressor, the part load capability of the unit is quite good. Means, let's say, over the widest range of the application. So we usually say that from 30% to 100% load, we can use the unit, and just at the outer edges, the efficiency drops a little bit, but in principle, it's really constant over the entire range of operation. Therefore, also part load operation is easily possible without any loss of efficiency. So if we look onto this chart here, or onto this table, you see the temperature range which we can achieve currently is at 160, 165, depending a little bit on the if we use steam or if we are producing steam or hot water. So with steam we can go to 165 to 160, with hot water to 165. We can go higher. This is not an issue. Currently we are limited by, at least when we use HFOs, we are limited by the fact that there is no HFO currently which can go higher. If we go to natural refrigerants, we also could come higher with the heat pump. We don't think that this is necessarily needed, but I will come later to this point. But it's possible. Yeah. So if you really would like to go to 200 degrees, it's possible also with a heat pump. Yeah. So we think, or the ThermBooster itself is PLC controlled, so it can remotely be controlled if the customer wishes to do so. We do more or less everything in Germany, or some parts will come from other countries in Europe, but it's made here in the EU definitely. We send it on one rig to the customer, and then it's more or less plug and play. So it's just a couple of connections and you go, so electrical connections and then a bit of piping and you can go. So if we talk about the ThermBooster, it's not one product, so it's a product range. So we say it's kind of a building kit. So if we start with the compressor, so we can build units which have one compressor, but we can also go to 2 or 3, or sometimes even 4 on one rig. We could do a one-stage solution or a two-stage solution. So when the temperature lift is more than maybe 70 degrees, we usually then go to a two-stage heat pump. On the evaporator side, we use usually plate heat exchangers, but if for the customer it's better to use different kind of heat exchangers because he wants to directly go with some, let's say, dirty fluids into the heat exchangers, we could go to other techniques. It's possible. It's not the standard, but it's possible if the customer wants. On the condenser side, we are using plate heat exchangers if we produce hot water or thermal oil. If we go directly into steam, we use this kind of plate and shell heat exchangers, so means it's nothing else than a pressure vessel with a plate package inside, yeah, there we can produce directly steam, which is, by the way, approximately 2/3 of the requests we are getting in is directly steam production. So now I will come to a couple of examples. So this is a unit which is currently still in our lab, but it will go into the gelatin production. So it's not gummy bear production, but we thought that it's a nice picture on. So it's a single compressor unit. We take as a heat source water from a CHP. So the CHP is using the exhaust gas to directly produce steam, but the cooling water for the engine can't be used at this customer. So it's wasted more or less. So in winter times they do a little bit of floor heating, but this is yeah, in most of the months not used. So we take this, cool it down to 70 degrees to cool the engine, and we are producing here 120 degrees steam, which is used to produce the gelatin. And yeah, with this one compressor, we have approximately 0.5 megawatt of heating power coming out at a COP of 4.4. Yeah, and so the CO2 reduction will be in the range of 550 tons. This is a picture of the unit as it was in our lab. So yeah. These are two other units which have gone to the company UBQ because it's not directly food, it's plastics industry. I don't go too deep onto this, but these units have been running in this facility, or they are running. Unfortunately, the customer is not really ready with his process, so it's just an on and off operation, so not a constant operation at this point in time, but this will come in summer this year. Another example from the food industry is a bakery. Unfortunately, they are waiting for the incentives from the German government, which are not yet granted. So we are also in a waiting position here, but this has been agreed. It's very similar applications also in combination with the CHP. So here the temperature level is a little bit higher and the steam demand is on a lower level. So it's just 1.5 bar steam, which means that the COP, so the efficiency goes up, and we have a higher power output. So you see we have two compressors built in here, which means that we produce 1200 kilowatts of heat in this application, and the emission which we avoid is 1.7 tons per year. Now a project which will be installed in summer. It's also not really food, but it's tobacco, and here we will install a unit. Yeah, it's currently under production, so it will be installed in summertime with a heating capacity of 600 kilowatts. It's a very high or relatively high temperature lift, so we are getting in with 50 degrees and need to cool it to 36 degrees. And then the temperature which we will produce is 140 degrees ish, or 139, but as steam. And yeah, so we always calculate from this lower point here to the steam temperature. So it's a temperature lift of 100 degrees, and for this COP of 2.3, I think is still acceptable. It's anyhow the question: do you calculate against gas or against an electrical boiler? If you go to an electrical boiler, it's clearly much more efficient. With gas, in some European countries, it's difficult then to justify just from the commercial point of view. But yeah, it's a question what you would like to achieve. And yeah, as a last project which I would like to show, it's again not really food. However, I would like to show it because I would like to show what's possible with a combination of techniques. So this is this so-called AHEAD project. It's an Austrian project where also the AIT, so the Austrian Institute for Technology, is involved. It's at the company Takeda, so a Japanese pharmaceutical company. And the interesting thing is, when I switch to the next slide here, that we can show here the entire production of heat in this company. So what they already have, and then what many companies do have, is a chiller system which is already existing. The heat from this chiller system goes into an ammonia heat pump, which is already also existing. From this ammonia heat pump, we will receive 70 degrees hot water. We will produce steam at 120 degrees, so 2 bars. And at the end, there is, in addition, an MVR system which brings the steam to 11 bar. We could go even higher if you would add another stage of MVR system there. So this means we can clearly see that also temperatures in the range of 200 degrees are possible to achieve without burning anything. We can simply do it with a combination of heat pumps and MVR also for the future. As I said, we also could, in theory, produce close to these 200 degrees also with a heat pump. The question is, does it make sense? Because you anyhow need more than one stage. And so, yeah, if one stage is needed, then clearly we can go to 160, 170 degrees or even higher. But then the heat source needs to be on a temperature level which is high enough to do so. So yeah, that's then the last slide which I would like to show. So here we just collected from the last couple of months all the requests which we have got in from the food industry, and you see that the requests are really coming from maybe not all over the world, but relatively widespread, and that we have requests which have a very high temperature lift, and therefore the COP is relatively small. But we have also requests where the temperature lift is very low, and therefore the COP goes really up. But this shows a little bit how the efficiency of a heat pump could be depending on the temperature lift. And this is, I think, the important thing. So in former time, or currently everybody thinks in steam boilers, and steam boilers work simply like you're boiling water, and once you have done the phase change from water to steam, you have used most of the energy. To get a little bit higher steam pressure doesn't cost you too much as additional gas, so it's just a little bit of the energy which you need to put in. If we think in heat pumps, we need to change how we think. Then we really need to see that we maybe go to a low temperature base network of heat and lift wherever it is needed the heat to a higher level, but just to the level which is needed, and not generally saying, okay, let's work with 11 bar of steam, and wherever we reduce the steam pressure. This is not efficient. Therefore, heat pumps need a little bit different thinking in the industry. Okay, so that's it. Thank you for your attention, and goodbye.